Welcome to Study Session 5, Introduction. The data collected in a study does not by themselves answer research questions or test research hypotheses. The data needed to be systematically analyzed to determine its trend and pattern of relationship. In this study session, therefore, you will outline the process of data analysis. You will also explain rationale behind statistics and main types of data. This is an all-important session as you will also see how to use statistics to test hypotheses. When you have studied this session, you should be able to 1. Outline the process of data analysis. 2. Discuss the reasons behind statistics and the main types of data. 3. Use statistics to test hypotheses. 4. Explain the steps in testing of hypotheses. 5. Determine which statistical tests are appropriate for analyzing your data for your resident research project and explain its procedure. 6. Explain the criteria to be met in the discussion of finding. Process of data analysis. There are 6 stages of the process. 1. Preparation of data for analysis. 2. Description of sample. 3. Testing the reliability of measurement method. 4. Exploratory analysis of data. 5. Confirmatory analysis guided by objective or hypothesis. 6. Post hoc analysis. Preparation for data analysis. 1. Start from data collection stage. 2. Serial numbering of instrument. 3. Coding. 4. Selection of software for data entry. Examples are SPSS, EpiInfo, Excel. 5. Understand the selected software. Use of sympathetic plan of data entry such that errors are minimized. Cleansing of the data. It is time consuming. It involves cross-checking every datum on printout with original datum. Identify incomplete data. Description of the sample. Complete picture of sample. 1. Frequencies of demographic variable. 2. Estimate of central tendencies, that is mean, and dispersion, that is SD standard deviation of variable relevant to describe the data, e.g. age. Ascertaining the reliability of measurement. 1. It is expected that reliability of the instrument be measured before collection of data. 2. The acceptable alpha coefficient is 0.7 to 1. 3. The researcher must make a decision and justify continuing if less than 0.7. Explanatory analysis. At this stage, the researcher makes effort to be familiar with the nature of data obtained on different variables in objective or research questions and relevant variables for hypothesis testing. This could be done using measures of central tendency mean median mode and measures of depression. This will help the researcher to identify outliers. Confirmatory analysis. After the use of explanatory analysis for understanding the sample, the researcher progresses to confirmatory analysis. Confirmatory analysis is performed to confirm expectations of hypotheses, and findings can be generalized from the sample to appropriate population. Post hoc analysis. This is the last step in the process of analysis. Confirmatory analysis such as chi-square, ANOVA may explain that there is difference among groups but may not specify which groups are different. Post hoc analysis will identify which groups are different. The reason behind statistics. There are certain theories or reasons we must understand about statistics. 1. Probability theory. Deductive explains the extent of a relationship, for example, the probability that an event will occur from an action, usually expressed as lowercase study p, and values expressed in percentages of values ranging from 0 to 1. For example, p is equal to 0.32 means there is 32% chance that a particular outcome will occur. It could also be expressed as p less than 0.05, which means that the probability that an event will occur is less than or equal to 5%. Probability values are used in reporting results of statistical analysis. 2. Decision theory, hypothesis testing, level of insignificance. It is inductive with the assumption that everyone in the group is the same. This is what is traditionally referred to as null hypothesis, e.g., there is no difference in the performance of students from schools of nursing and department of nursing at the NMCN examinations. In order to test the null hypothesis, there must be a cutoff point set before commencing data collection. The cutoff point is referred to as level of significance. The level of significance is the probability level at which the results of statistic analysis are considered to show a statistically significant difference between the groups. The level of significance is set at 0.05. Then, if the result of analysis is less than or equal to 0.05, then there is a significance difference. The value is absolute, hence, even if the analysis result is e.g. 0.51, when level of significance was set at 0.05. Note that from the point of view of decision theory rules, 0.001 is not considered more significant than 0.05. This is because level of significance is dichotomous, that is, it is either significant or not significant. Hence, highly significant is not acceptable from the point of view of decision theory. However, from the point of view of probability theory, there is considerable difference in the risk of regarding the null as true when it is false. Type 2 theory. P is equal to 0.05 and P is equal to 0.001. If P is equal to 0.05, then the probability of the groups belonging to the same population is 5 in 100. And if P is equal to 0.001, it is 1 in 1000. P-value indicates the risk of type 2 error, while alpha indicates whether the probability value of a particular analysis met the cutoff point for deciding whether there is significant difference. When decision theory rules are applied to interpreting results of statistical procedure, probability that inferences are accurate increases. When information is applied to a general situation from a specific instance, it is referred to as generalization. Generalization and inference used in the inductive reasoning. Inductive reasoning implies that inference is made from specific case to general truth, from a part to a whole, from concrete to abstract, from specific sample to a more general population. In research, from study findings of a specific sample to a more general population. Hence, the researcher can conclude that there is no significant difference between two groups. Findings can also be generalized from samples studied to a larger population. 1. The normal curve is an expression of statistical theory. Developer is Johann Gies, an 18-year-old mathematician. It was developed in 1795. He found that repeated measurement in many samples from the same population is more accurate representation of the pattern of the curve than with only one sample. Draw the normal curve on board and then explain. 95.5% of the values are within two standard deviations. This means that there is approximately 95% probability that a given measure value will fall between two standard deviations of the population mean, and 5% probability that the values will fall in the tails of the normal curve, that is, below -2 and above +2. If significantly different one of the groups, when samples are not significantly different, it means they are from the same population, then it falls within the 95% range of values. If significantly different one of the groups will be within 95% range of values and the other outside. Talliedness. Non-directional hypothesis assumes that an extreme score is possible at either tail, hence it is referred to as two-tailed significant test. There are two means. Directional hypothesis, on the other hand, is referred to as one-tailed, and usually state that the extreme score is higher or lower than that of the 95% of the population. Use the drawings to explain. Significant knowledge of the situation is required to be able to determine whether the statistical value of the considered will be above or below the mean. One-tailed is more powerful than two-tailed hypothesis as it decreases the risk of type 2 error. Type 1 and type 2 error. Type 1 error occurs when the null is rejected when it is true. There is greater risk of type 1 error with 0.1 level of significance than with 0.1 level of significance. It is vice versa with type 2 error, which occurs when the null is considered to be true when it is not. Type 2 errors are usually due to flaws in research methods. 3. Power. Controlling of risk of a type 2 error. This is the probability that a statistical test will detect a significant difference that occurs. Cohen 1988 considered that four parameters of significance: sample size, power and effect size. If three are known, there is formula to work out the fourth. The minimum power level acceptable is 0.80. Level of significance and sample is determined by researcher. Effective size, that is, degree to which the phenomenon is present in the population or the degree to which the null is false. 4. Degree of freedom is the degree of a score value to vary given the other existing values and establish sum of the score. In statistics, the number of degrees of freedom is number of values in the final calculation of statistics that are free to vary. Types of data. What is data? From the search point of view, information gathered is referred to as data. There are two main types. 1. Qualitative data. Verbal narrative pieces of information measured on nominal or ordinal scale, categories or attributes, and there is no notion of numerical magnitude. 2. Quantitative data. Information in numerical form measured on at least the interval scale and measurement are in numerical values. It can be discrete or continuous. Discrete if integer values only, e.g. Apgar score, and continuous if it can assume any value between any 2 points of the real line, that is, e.g. weight, height, skin fold thickness. The response of the sample of the study collectively is the data of the study. Data analysis is the process of organizing, synthesizing, evaluating, and interpreting information or data. Research variables. The concept which is of interest to the researcher is a variable. A variable varies, that is, takes on different values. Examples of variables in a study: age, blood pressure, pulse rate, height. The variables collected from the data, the researcher is interested in the variation between people and the relationships between them. Types of variables. There are various ways to characterize a variable for the purpose of analysis. 1. The role of variable in research. Dependent and independent variable. 2. The nature of the variable. Discrete and continuous variables. Independent variables is the hypothesized cause of influence on the dependent variable. For example, in this research question, does students' learning style influence scores in examinations? Does school type influence student nurses' performance at the Nursing and Midwifery Council examination? Classification of statistics. Two broad classifications. 1. Descriptive. 2. Inferential. Uses of descriptive data. Some of the major reasons are: 1. Becoming familiar with the data set. 2. Cleaning the data. 3. Inspecting data for missing values, that is, rectangular matrix, data for all members for all key variables. Examine cumulative extent of missing variable. 4. Testing assumptions for statistical tests. Statistical tests are based on a number of assumptions. 5. Assumption is a condition that is presumed to be true and when violated can lead to misleading or invalid results. There are 4 groups of descriptive statistics. 1. Measures to condense data. 2. Measures of central tendency. 3. Measures of variability. 4. Measures of relationship. The first 3 are referred to as univariate statistics, while the last falls under bivariate when more than 2 variables are involved. However, it is referred to as multivariate. Measures to condense data. There are statistics used in the analysis of large amounts of data, such as the large data are condensed into a more understandable form. These include: 1. Frequency distribution. 2. Frequency count. 3. Graphic presentation. 4. Percentages. Frequency. Frequency count by simply counting the number of occurrences of each observation. It is appropriate for nominal and ordinal data. This is commonly done by a slash across serves as fifth occurrence. This is repeated until all observations are counted. From frequency count, a frequency table could be drawn. Frequency distribution could be grouped or ungrouped, which is an ordered display of each value in a data set together with its frequency. That is the number of times that value occurs in the data set. They are often also presented as relative frequencies, that is, as proportions or percentages of the total number of individuals. For example, method of delivery of 600 babies born in a hospital. Method of delivery, number of births, percentage. Method of delivery, normal, number of births, 478, percentage, 79.7. Method of delivery, forceps, number of births, 65, percentage, 10.8. Method of delivery, cesarean section, number of births, 57, percentage, 9.5. Total, 600, percentage, 100.0. Ungrouped frequency distribution. Ungrouped data are usually categorically data such as gender, marital status, education, etc. It is usually used to discrete rather than the continuous data, e.g. gender, ethnicity, marital status. Grouped frequency distribution. When range of scores is large, then it could be grouped before counting the frequencies. Grouped frequency distributions are used when continuous variables like age, weight are used. Groups of scores in a frequency distribution are referred to as class intervals. The intervals are chosen arbitrarily, but most meaningfully, classification should be used. Rules governing classification system. There should be at least 6 and not more than 20 groups. Rulings governing classification system. There should be at least 6 and not more than 20 groups. The class must be exhaustive. Each datum must fit into only one class, e.g. 10 to 20, 21 to 30, 31 to 40. However, there are expectations to the rule occasionally when you make the upper and lower limits open, e.g. below 20,000 naira and upper limit above 40,000 naira. Class intervals could be in units of 3, 5, 10, etc. Percentage distribution. This indicates the percentage of sample whose scores falls into a specific group. It is useful in comparing the data with data from other studies with varying sample sizes. Cumulative distribution is a type of percentage in which the percentage of and frequencies of scores are summed up as one moves from top of the table. The bottom category should add up to total sample size and 100%. Graphic presentation of frequency distribution. Frequencies and relative frequencies are commonly illustrated by a bar chart, also known as a bar diagram, histogram, or a pie chart. Graphic presentations make data more visible. Bar graph is a figure used to represent frequency of nominal or ordinal data. Bar graph is very useful when categories are qualitative rather than numerical data. The bars may be drawn in horizontal or vertical direction. The bars do not touch each other, indicating that they are separate categories. Histogram. This is a graph that uses bars to represent frequency distribution of variables measured at ordinal, interval, or ratio level. The bars are of equal width and they touch each other, therefore indicating that they are on a continuum. The width of the bar is determined by the class interval. The height of the bar represents the frequency of the occurrences of each class interval. Drawing a histogram. 1. Two axes are drawn, horizontal and vertical lines are drawn. 2. Vertically, axis. The vertical y-axis is called the ordinate, while the horizontal axis is called absciscal. From 0, the ordinate is marked at equal intervals. The horizontal is marked off according to class intervals. The vertical axis is drawn to third of the length of the horizontal for good graphic proportions. Frequency polygons. This is a graph that uses dots connected with the straight lines to represent distribution of intervals or ratio data. A dot is placed above the midpoint of each class interval. The points are joined. It represents a frequency distribution and usually constructed from a histogram. Construction of a frequency polygon from a histogram. Pie chart. It is used to show the components of a total and more intelligent visual impression sometimes. Draw a big circle to represent total observations. Divide circle into sectors according to the frequency of each attribute. Use bracket small letter n over capital letter N times 3,600 to represent each sector. Shade sectors in different colors to distinguish each segment. Frequency distribution by shapes. It could be classified as symmetrical or non-symmetrical. Symmetrical distribution have equal halves. Both sides of the midpoint are the same. Non-symmetrical are also referred to as skewed. The highest point of distribution is not at the center. If the tail points to the right, it is considered to be positively skewed, e.g., personal income, and if to the left, negatively skewed. Summary indices. A frequency distribution gives a general picture to the distribution of a variable. It is often convenient, however, to summarize a numerical value still further by giving just two measurements, one indicating the average value and the other the spread of the values. This includes the measures of central tendency and measures of depressions. Measures of central tendency, usually referred to as an average in layman's terms. It is the most concise way of describing the data. It summarizes a frequency distribution by use of a single number. Central means midpoint, and tendency refers to general trend of the number to cluster in a particular way. Three commonly used are the mode, median, mean. Mode. Mode is the most occurring value or score from a list of scores, that is, one with the greatest frequency, unimodal. When categories are involved, it is referred to as a model class. It is the appropriate MCT for nominal data. It may also be used for ordinal, interval, or ratio data. When we have two modes, it is referred to as a bimodal. When more, it is multimodal. Rarely reported in literature because it is a crude estimate of the average. Median. It is the value of the exact central of an ungrouped frequency distribution. When percentiles are being calculated, it is the 50th percentile. To obtain the median, it is need to rank order the scores. If the number of scores are odd numbers, then you have half of the score above and half below. If even the median is the average of the two middle scores, then it is not an actual score in the data. It is the most appropriate MCT for ordinal data, but it can be used for interval and ratio data. It is the best measure of central tendency when data is skewed. The median is not affected by extreme variables. It is usually used to report average income. Median is equals to bracket n plus 1 value of the ordered observation. If group data from frequency distribution is being used, then you use this formula to calculate the median. MD is equals to LL plus IN over 2 minus FC. Mean. The mean is the average sum of a set of values found by adding all values and dividing by total number of values. It can be referred to as the arithmetic mean. Unlike the mode and the median, which indicate the position of certain values in a distribution, the mean takes into consideration all values. It is the most stable MCT for interval and ratio data if the distribution is normal. Mean is equal to sum of all observations over number of observations. The formula for calculation of the mean is x is equals to sum of xi over n. The mean is usually the preferred measure since it takes into account each individual observation and is most amenable to statistical analysis. The median is a useful description measure if there are one or two extremely high or low values, which would make the mean unrepresentative of the majority of the data. The mode is seldom used if the sample is small. Either it may not be possible to estimate the mode, or the estimate obtained may be misleading. The mean, median, and mode are on average equal when the distribution is symmetrical and unimodal. When the distribution is positively skewed, a geometric mean may be more appropriate than the arithmetic mean. Measures of variability or measure of dispersion. They describe the spread of values in a distribution, that is, illustrate with two distributions of pulse rates with same mean. 87 plus 77 plus 76 plus 76 plus 74 is equal to 390 divided by 5 is equal to 78. 100 plus 90 plus 80 plus 70 plus 50 is equals to 390 over 5 is equal to 78. Though the two groups have same mean, they are not similar. Group A is homogeneous while group B is heterogeneous. The most common measure of dispersions are range, percentile, variance, standard deviation, the z-score or standardized score, scatter plots. Range. It is the difference between the highest score and the lowest score in a group of values. It is the simplest measure of variability. It is represented as a single number, that is, if the highest score is 50 and the lowest score is 15, the range is 35. It can be used to have quick glance of the spread of a data. It is crude and very sensitive to outliers. It is, however, limited in its usefulness, as one extreme score can change the range drastically. Range is equal to highest value minus lowest value. Interquartile range. The interquartile range helps to correct the influence of extreme scores. It contains the mid-half of the value in the frequency distribution. Interquartile range is equal to upper quartile minus lower quartile. IQR is equal to Q3 minus Q1. Q3 is the point below which 3/4 of the population lies. Q1 is the point below which 1/4 of the distribution lies. Semi-quartile range is found by dividing the quartile range by 2. Percentile. A percentile is a score value above which and below which a certain percentage of the distribution falls. E.g., P30 shows that 30% of the values is below that point. It is a common statistic used to allow comparison with others. Standard deviation. The standard deviation is the mean of the spread in a set of observations. It is the most widely used measure of variability when interval and ratio data are concerned. It is abbreviated SD or small s hyphen. It indicates the average deviation or variation of all values in a set of values from the mean data of those values. Standard deviation practical example. The formula is S is equals to square root formation into bracket x1 minus x close bracket raised to power 2 over n minus 1. Example on standard deviations. The number of crises experienced by 5 sickle cell patients in a year are 3, 0, 2, 1, 4. Find the mean, variance, and standard deviation. Mean is equals to formation xi over n is equals to 3 plus 0 plus 2 plus 1 plus 4 over 5 is equals to 2.0. Variance. Formation into bracket xi minus x close bracket raised to power 2 over n minus 1, which is equals to open bracket 3 minus 2 close bracket raised to power 2 plus open bracket 0 minus 2 close bracket raised to power 2 plus open bracket 2 minus 2 close bracket raised to power 2 plus 1 minus 2 close bracket raised to power 2 plus open bracket 4 minus 2 close bracket raised to power 2 over 5 minus 1. which is equals to 1 plus 4 plus 0 plus 1 plus 4 over 4 is equals to 10 over 4, which is equals to 2.5. Standard deviation is equals to square root formation in open bracket x minus I minus x close bracket raised to power 2 over n minus 1, which is equal to square root 10 over 4 is equal to 10 over 2 is equals to 1.58. Note, calculators are available to do this. Uses of central tendency and variability index. For variables measured on an interval or ratio scale for many ordinal level variables too, there are routine use central tendencies and variability index. 1. Answering research questions. 2. Understanding the data. 3. Describing the research sample. 4. Addressing the missing data problems. When there are missing data, a decision needs to be made on how to handle the issue. 5. Addressing the missing data problems. When there are missing data, a decision needs to be made on how to handle the issue. You may drop the case. You may drop the variable. These are extreme solutions which should be avoided. You may perform a mean substitution, that is, calculate means based on available data. Tips on preparing tables with central tendency and variability index. Two separate tables may be necessary when presenting nominal variables, that is, index percentage, and ordinal or ratio level mean using mean and standard deviations. However, when presenting background information, this may be mixed or socio-demographic variables. Put variable names in the row and figures in columns. Report means and standard deviations to 1 or 2 decimal points. There are no specific rules for ordering the variables that appear in the table, but researcher may put order. Means and standard deviations may be represented using 2 different columns, or 26.2 bracket 2.8 close bracket, or 26.2 plus 2.8. Sometimes additional information may be presented on the table depending on the variable in question. Differential statistics. Descriptive statistics are useful for summarizing data, but usually researchers do more than simply describe. Inferential statistics can be used to prove or disprove theories, determine associations between variables, and determine if findings are significant and whether or not we can generalize from our sample to the entire population. Inferential statistics, which are based on law of probability, provide a means for drawing conclusions about a population given data from a sample. This is the procedure by which we reach a conclusion about a population on the basis of the information contained in a sample drawn from that population. It has 2 broad areas, which are estimation of parameters and hypothesis testing. Estimation of parameters. The major purpose or objective of biomedical or health research could be to estimate certain population characteristics, which can be quantitative, such as average systolic blood pressure of adult men, and qualitative, such as proportion with certain health condition. It can be point or interval estimate. 1. Point estimate. A single numerical value used to estimate the corresponding population parameter. 2. Interval estimate. Consists of numerical values, defining a range of values that, with a specific degree of confidence, we feel includes the parameters being estimated. These are intervals supposed to contain true estimates of the population parameters with a degree of confidence. Components includes estimator plus reliability coefficient times STD error. The estimator refers to the point estimate, that is, mean or proportion. 2. The reliability coefficient depends on the desired degree of confidence. 95% is common. Normality of the data contribution. sample size. The quantity, that is reliability coefficient times STD error, is called the precision of the estimate or margin of error. When sampling from a normal distribution with a known variance, an interval estimate for the mean may be expressed as sample mean plus z bracket open bracket 1 minus alpha over 2 close bracket alpha over square root of n, where z into bracket 1 minus alpha over 2 is the value of z to the left of which lies 1 minus alpha over 2 and to the right of which lies alpha over 2 of the area under the curve. At 68%, 95% and 99% confidence levels, z into bracket 1 minus alpha over 2 close bracket is 1.0, 1.96, 2.58 respectively. Use of confidence interval. Confidence interval is a range of likely values for an unknown population parameter at a given confidence level. 2. Provides uncertainty attached to sample estimate on account of sampling error. 3. Only by convention that the 95% confidence level is commonly chosen. 4. CI statistics plus 1.96 SE statistic. 5. 95% of confidence intervals from repeated sample estimates contains the true population means. Tell us by how much an exposure affects the subject. Focus is on range of values to be considered plausible for the population. Convey information on the magnitude of the differences in, say, blood glucose levels between diabetic and non-diabetic patients. Gives estimates of difference in, say, glucose levels that would have been obtained if total population were studied. Hypothesis. Hypothesis is a statement or concept about a phenomenon that has not been verified. It is also defined as statement about an expected relationship between two or more independent variables and one dependent variable. Types of hypothesis. It includes research hypothesis, which is the supposition that motivates the research, and statistical hypothesis, which are stated in such a way that may be evaluated by appropriate statistical techniques. It is a statement of fact yet to be tested. Hypothesis testing is the procedure for investigating, verifying whether these statements are true. It can be stated as a negative or positive statement. Null hypothesis, alternative or declarative hypothesis. Steps in hypothesis test. 1. Statement of the null hypothesis (HO). 2. Statement of the alternative or declarative hypothesis (H1 or HA). 3. Statement of level of significance. 4. Choice of appropriate test statistic. 5. Numerical evaluation of test statistic. 6. Decision to reject or not reject (HO). The null hypothesis (HO) states that there is no relationship between independent and dependent variables. It is the hypothesis to be tested and is usually stated in a way that does not prejudged. It is also referred to as the hypothesis of no difference, no association, no effect, and it is either rejected or not rejected. The alternative or declarative hypothesis (H1 or HA), it provides objective criteria for deciding whether a hypothesis should be accepted as true or rejected as false. This is a statement of what the researcher believes is true. If the sample data cause a rejection of the HO, it is usually the same as the research question or hypothesis, and it is a state of inequality. Choice inferential statistical tools based on statement of hypothesis. 1. Test of association between independent and dependent variables, use of chi-square. 2. Test of differences in the means of the two groups of values of variables use t-test. 3. Test of difference in the means of groups of values of variables that are more than 2, use ANOVA. Errors of hypothesis test. Type 1 error. An investigator makes a type 1 error by rejecting the null hypothesis when it is in fact. Type 2 error. This is the error committed when we fail to reject the null hypothesis, when in actual fact it is false. The actual situation is that the null hypothesis is true or false. True, null accepted, correct decision. False, type 2 error. True, false or null rejected, type 1 error. False, correct decision. Level of significance is the phrase used to signify the probability of making a type 1 error. The two most frequently used levels of significance, that is referred to as alpha, are 0.05 and 0.01, also called p-value or type 1 error. It is also defined as the maximum probability of committing type 1 error or the chance of wrongfully rejecting the null hypothesis. A small p-value, that is less than a pre-specified value, usually 0.05, leads to the rejection of the null. Naturally, researchers would like to reduce the risk of committing both types of error. Unfortunately, lowering the risk of a type 1 error increases the risk of a type 2 error. The stricter the criterion for rejecting a null hypothesis, the greater the probability of accepting a false null hypothesis. However, researchers can reduce the risk of a type 2 error simply by increasing their sample size. Power of a test is its ability to reject null hypothesis when it is false. Choice of test statistic. Within a hypothesis testing framework, the researcher uses studied data to compute a test statistic. It is computed from the data to enable comparison with percentage points of the appropriate distribution, and the choice depends on 1. Study objectives, that is elimination or comparison. 2. Study design, a dependent or dependent sample. 3. Variables, data type, quantitative or qualitative. 4. Sample size and sampling method, random or not. 6. Sampling distribution. The choice of test statistics serves as the decision maker because the decision to reject or not reject HO depends on the magnitude of the test statistics. General formula: test statistics is equal to relevant statistics minus hypothesized parameter over standard error of relevant statistics. Test statistic decision rule. Researchers reporting the results of hypothesis tests state that their findings are statistically significant. The word significant should not be read as important or meaningful. In statistics, the term significant means that the obtained results are not likely to have been due to chance at some specified level of probability. All possible values that the test statistic can assume are divided into two groups by a critical value. 1. Those in the rejection region are above the critical value and are less likely to occur if the HO is true. And 2. Those in the non-rejection region are below the critical value and are more likely to occur if HO is true. Rule: reject HO if the value of the test statistic computed from the sample is greater than or equal to the critical value. Do not reject HO if the computed value of the test statistic is less than the critical value. Types of statistical tests. There are two types of parametric tests and non-parametric tests. Parametric tests are more powerful than non-parametric tests and are generally preferred when variables are measured on at least the interval scale. Parametric tests are characterized by three attributes. 1. They focus on population parameters. 2. They require measurement on at least an interval scale. 3. They involve other assumptions about variables under consideration, such as assumptions that the variables are normally distributed in the population. The most common distribution assumed is the normal distribution, and examples are z-test, t-test, and f-test analysis of variance. Non-parametric test, in contrast, does not any distributional assumption about the underlying variable in the population and is appropriate for skewed data, graded responses, and analysis requiring little or no assumptions about the underlying variable. Examples include Mann-Whitney U, Krusaki-Wallis, chi-square test, Wilcoxon signed rank test, etc. Settling the appropriate test statistics for tests involving two or more samples. Relationship between two quantitative variables. Use 1. Correlation analysis, that is the strength of relationship. 2. Linear regression analysis, that is the prediction of one variable from the other. 2. Relationship between qualitative variables using 3. If more than two group analysis of variance and ANOVA. The types of inferential statistics we'll go over: correlation, t-test or ANOVA, chi-square, logistic regression. Overview of statistical tests. Correlation. When to use it. When you want to know about the association or relationship between two continuous variables. Example, food intake and weight, drug dosage and blood pressure, hair temperature and metabolic rate, etc. What does it tell you? If a linear relationship exists between two variables and how strong that relationship is. What do the results look like? The correlation coefficient is equal to passing R, ranges from -1 to +1. Guide for interpretation strength of correlations. 1 to 0.25, the little or no relationship. 0.25 to 0.50 is equal to the fair degree of relationship. 0.50 to 0.75 is equal to the moderate degree of relationship. 0.75 to 1.0 strong relationship. 1.0 perfect correlation. How do we interpret it? If R is positive, high values of one variable are associated with high values of the other variable. That is, both go in same direction, up or down. Example, diastolic blood pressure tends to rise with age. Thus, the two variables are positively correlated. If R is negative, low values of one variable are associated with high values of the other variable, opposite direction, up down or down up. Example, heart rate tends to be lower in persons who exercise frequently. The two variables correlate negatively. Correlation of 0 indicates no linear relationship. How do you report it? Diastolic blood pressure was positively correlated with age, bracket R is equal to 0.75, P less than 0.5, close bracket. Tip. Correlation does not equal causation. Just because two variables are highly correlated, this does not mean that one causes the other. When to use them? Paired t-test. When comparing the means of a continuous variable in two non-independent samples, that is, measurements on the same people before and after a treatment. Examples: 1. Is diet X effective on lowering serum cholesterol levels in a sample of 12 people? 2. Do patients who receive drug X have lower blood pressure after treatment than they did before treatment? Independent samples t-test. To compare the means of a continuous variable in two independent samples, that is, two different groups of people. Examples: do people with diabetes have the same systolic blood pressure as people without diabetes? 2. Do patients who receive a new drug treatment have lower blood pressure than those who receive a placebo? 6. If you have greater than two different people, you use ANOVA, which compares the means of three or more groups. What does a t-test tell you? If there is a statistically significant difference between the mean score or value of two groups, or either the same group of people before and after, or two different groups of people, what do the results look like? Students C. How do you interpret it? By looking the corresponding p-value. If p is less than 0.05, means are significantly different from each other. If p is greater than 0.05, means that they are significantly different from each other. Chi-square. When to use it? When you want to know if there is an association between two categorical, that is nominal variables, that is, between an exposure and outcome. Examples: 1. Smoking, yes or no, and lung cancer, yes or no. 2. Obesity, yes or no, and diabetes, yes or no. What does a chi-square test tell you? If the observed frequencies of occurrence in each group are significantly different from expected frequencies, that is, a difference of proportions, what do the result looks like? Chi-square test statistics is equal to x2. How do you interpret it? Usually, the higher the chi-square statistic, the greater likelihood the finding is significant, but you must look at the corresponding p-value to determine significance. Tip: chi-square requires that there be 5 or more in each cell of a 2 times 2 table and 5 or more in 80% of cells in the larger tables. No cells can have a zero count. Logistic regression. When to use it? When you want to measure the strength and direction of this association between two variables, where the dependence or outcome variable is categorical, e.g., yes or no. When you want to predict the likelihood of an outcome while controlling for confounders. Examples: examine the relationship between health behavior, smoking, exercise, low-fat diet, and arthritis versus no arthritis. 2. Predict the probability of stroke in relation to gender while controlling for age or hypertension. What does it tell you? The odds of an event occurring, the probability of the outcome event occurring divided by the probability of it not occurring. What did the result look like? Odds ratios, take 2. Odds ratios, OR, and 95% confidence intervals, C high. How do you interpret the result? Significance can be inferred using by looking at confidence intervals. If the confidence interval does not cross 1, e.g., 0.04 to 0.08 or 1.50 to 3.49, then the result is significant. If OR is greater than 1, the outcome is that many times more likely to occur. The independent variable may be a risk factor. 1.50 is equal to 50% more likely to experience event or 50% more at risk. 2.0 is equal to twice as likely. 1.33 is equal to 33% more likely. If OR less than 1, the outcome is that many times 2. Many times less likely to occur. The independent variable may be a protective factor. 0.50 is 50% less likely to experience the event. 0.75, that is equals to 25% less likely. Discussion of findings. The researcher will not stop at merely stating the findings of the study. The meaning of the study must be conveyed to the reader, who will want to know the application of the obtained result. He will want a general understanding of the subject matter and the related areas. This makes the decision of findings very important, and this is why it usually accompanies the report. Sometimes the researcher may combine the discussion with the findings, and at other times it may constitute a separate chapter or section of the report. Whatever method he chooses to handle the discussion, the following criteria must be met. 1. Drawing inferences from findings. Inferences are drawn from the particular study to the general population, target population. The researcher's knowledge of the subject matter, aided by a thorough review of literature, will have a tremendous influence on his efforts. He can draw the inference at any stage, relying on his theoretical knowledge of the research, his ability for abstract thinking to help him do this. 2. Stating limitations of the study. The researcher should note that he may not solve any problem by his study. He should know that the conditions of the study that limit the extent of legitimate organizations. 3. It should alert the reader to the particular characteristics of the sample and the possibility that the sample might differ from the general population. It must also let the reader know the specifics of his method that might have influenced the outcome of the study. 5. It is important that he states all other factors that he is aware of that might have operated to produce an atypical result. 6. Treatment of unanswered questions. The researcher must include in a discussion all questions that have been left unanswered by the study or new questions which the study has raised. 7. It will state whether replicating the study or redesigning it with different sample and or instruments might answer the question. You may also want to say whether a different method would be used in the next study. 8. Explain the meaning of information in easily understood terms. 9. Discuss how reliability and validity were maintained. 10. Discuss the weakest links, that is, no true confession. Discuss the results in terms of whether they were significant and in keeping with those predicted. Not significant. Explain. Significant but opposite to those predicted. Mixed results. Unexpected or serendipitous. It should compare results to previous studies. It should discuss statistical and clinical significance. Most experts would want to admonish beginning researchers to be cautious when they reach the point of discussing their findings, drawing calculations, or making recommendations. It is very important that researchers point out and discuss the possible meaning of the findings evidenced by their data. They should resist the temptation to make recommendations that cannot be supported by the results of their study. Study session summary. In this study session, you learned that descriptive statistics can be used with nominal, ordinal, interval, and ratio data. Frequencies and percentages describe categorical data, while standard deviations describe continuous variables, while inferential statistics can be used to determine associations between variables and predict the likelihood of outcomes or events, and inferential statistics tells us that if our findings are significant and if we can infer from our sample to the larger population. The data needs to systematically analyze to answer the research questions and hypotheses, and steps of testing hypotheses for each statistical test is the same. This is the end of study session 5.